So hello everyone again. This is lecture 7 part 2 of wave optics. In the previous lecture we were discussing about a double slit experiment in the diffraction concept. Let's move on with the further discussion over that only. We will after this we will go to resolving power of some instruments and then we will move on to polarization. So I am Sameer Lavankar. Let's begin our discussion. Okay, so first of all, a course outline for you. We started with the introduction concept of wave optics, then went on to Huon's principle about wavefront, then the refraction and the reflection principles were being proved in the using the Huon's principle and wavefront concept. Then after this we went on to fourth concept, that is coherent and incoherent addition of waves, in which we understood the concept of intensity being maximum or intensity being 0. After that we went to a small concept called as Doppler effect. After the completion of fourth concept, we went on to interference of light waves. What is the interference of light waves? What is the Young's experiment? Why the phases are needed to be logged when the Young's experiment is being performed? Then in the sixth, now we are in the sixth concept, that is diffraction. In diffraction we understood the concept of why is there a bending of light occurring only when the obstacle is very small. We understood the single slit, why the intensity keeps on decreasing when the path difference is increased, and why there is a dark fringe when the path difference is equal to lambda by 2 or n lambda by 2. Similarly, now we are on the point of double slit experiment, in which we are understanding the concept of double slit is nothing but a superposition of two different single slit diffraction patterns. So now just let's move on to that concept only. So this was the final concept we are understanding. A double slit experiment is nothing but a pattern which is actually a superposition of single slit diffraction from each slit or hole. And as we also understood this concept, that the value of broad diffraction peak depends on the ratio of d by a, and when the value of a is keep on decreasing, then at some point the diffraction pattern will become flat and we will observe the two slit diffraction pattern. So now let's move on with the further discussions now in regarding double slit only. So in the double slit experiment, what will happen if we close one slit? So what will happen if we close one slit? Maybe it be same as a single slit diffraction pattern, or it will change. So you will see that it now amounts to a single slit, quite evident it will be a change to single slit. So this thing is done, this thing is done, but you will have to take care of some shift in the pattern. So as it is quite evident, let me draw it by say a 3D pattern. So let us suppose So let us suppose this is the scenario being talked about here. So for the Young's double slit experiment, there are two slits. Let me denote the two slits as S1 and S2. And similarly, an interference fringe will be, and interference fringes will be formed. Let me write the interference fringes as IF here. Interference fringes will be formed on the screen here. So now what will happen is, the scenario being talked about here is, let's say we close one slit. So what will happen? Let me change the color. Let's say there is no slit here. This slit is being closed now, there is no slit here. What will happen with the interference fringes scenario here? So for previous scenario, what was happening is, because it was symmetrical, the complete light which was coming from this direction and then moving on to these two places, and everything which was formed on the screen was symmetrical. But this time, because one of the slit is not available, there will be an unsymmetrical passage of light. So due to this unsymmetrical passage of light, there will be a shift in the interference pattern which is visible on the screen. So this is the only concept which we need to convey. So quite evident, because of this unsymmetrical direction only as the pathway, let us suppose that this is the first screen, this is the slit, and then there is another screen, means two slits were kept like this. Then because after this slit there is a passage of light going in two directions like this, But if we close one slit, let's say this slit is closed now, then only a unsymmetrical passage, only one direction passage is moving on, and therefore due to this an interference fringe is formed on the screen. Because of this unsymmetrical passage of light, there is a shift in the screen, a shift in the what we can say, shift in the screen's visibility of interference fringes. So therefore, but you will have to take care of some shift in the pattern, so hence there will be a shift. So why there will be a shift, I explained to you using diagram here. We now have a source at S and only one hole, which is either S1 or S2. So these are the S1 or S2 being talked about here. This will produce a single slit diffraction pattern on the screen, quite evident. It will produce single slit diffraction pattern. A single slit diffraction pattern is nothing but the intensity of central bright fringe being maximum, and then it keeps on decreasing as the path difference keeps on increasing. The center of the central bright fringe will appear at a point which lies on a straight line SS1 or SS2 as the case may be. So this line is nothing but, let me take a different color for this. So let us suppose for our scenario the value S1 is closed and S2 is open. So in this case what will happen is the central bright fringe will be formed at some location which is kept here. And let us suppose in another scenario we are taking a case in which the value of S2 was closed and S1 was open. Let us suppose for another scenario this S2 was being closed, then at that point the central bright fringe will be formed at some this location. And actually if both slits were being open, and then the central bright fringe would have been formed at somewhat this point. So as you can see, quite evident that there is some shift. This is the shift being talked about here. So either the shift would happen in this case here, or the shift would happen in this case here. So this is the shift being talked about in the explanation written on the left hand side. So let us move on. The center of the central bright fringe will appear at a point which lies on a straight line. It is quite evident if we write it as S. So it is at some either SS2 or either SS1. So this is the concept being talked about here, which lies on the straight line SS1 or SS2 as the case may be. We now compare and contrast the interference pattern with that seen for a coherently illuminated single slit, usually called single slit diffraction pattern. So hence we can see what is the comparison between different interference patterns. So the interference pattern has a number of equally spaced bright and dark bands. Quite evident, we know that it is nothing but a combination of bright and dark bands. How are these bright and dark bands appearing? This is one of the example of interference fringes being formed. So these are, as you can see, some are central bright fringes and then it is followed by dark fringes. Okay, so the interference pattern has a number of equally spaced bright and dark bands. The diffraction pattern has a central bright maximum which is twice as wide as the other maxima. So what happens in single slit, always what happens is there are diffraction, the central bright fringe has the value which is twice as wide. So let us say if the, let us say this is the denotation we talked about here. So the value of this is 2W if we consider another case scenarios here. So the value of width is twice for this case, for the central bright fringe. This is the concept we talked about here. So diffraction pattern has a central bright maxima which is twice as wide as the other maxima. The intensity falls as we go to the successive maxima anyway away from the center on either side. So this was the complete concept we understood in the previous lecture when we were talking about the single slit, that the intensity keeps on decreasing because the amount of width which is contributing to the bright fringes keep on decreasing as the value of theta increases. It is for central bright fringe it is maximum for it is A, then for next it is A by 3, then it is A by 5, then it is A by 7 and so on. Next is we calculate the interference pattern by superposing two waves originating from two narrow slits. So this is the interference pattern, that is how we can understand the concept of double slit experiment using single slit diffraction pattern. We calculate the interference pattern by superposing the two waves originating from the two narrow slits. The diffraction pattern is a superposition of a continuous family of waves originating from each point on a single slit. So this is a simple explanation. What we understood that diffraction, what is diffraction? So initially the explanation of diffraction was that diffraction is nothing but the bending of light. Diffraction is a phenomenon due to which light bends around a corner due to only when the obstacle is of the order of wavelength of light. Similarly, we understood what is diffraction pattern. Diffraction pattern is nothing but a superposition of a continuous family of waves originating from each point on a single slit. So diffraction occurs when the single slit experiment is being done. Next, for a single slit of width A, so it is a similar case scenario of single slit only. a single slit of width is the first null of the interference pattern occurs at an angle of lambda by a. So we know that a dark fringe is observed, so for this null is nothing but a dark fringe observed. This dark fringe is observed. At the same angle of lambda by a, we get a maximum for two narrow slits separated by a distance a. So what does it try to say is, let us say we are taking a single slit case. We are taking a single slit case and similarly we are taking a double slit case. So as the screen is same, only the value of the area which is slit difference is same, either it is 1 or it is 2. Then what is happening is, for the value of theta is equal to lambda by a, here for theta equal to, let me write theta here, for theta equal to lambda by a, here a dark fringe is occurring. Here it is a dark fringe, but in double slit it's a bright fringe. So this is the case being talked about here, that for a single slit of width, the first null of the interference pattern occurs at an angle of lambda by. At the same angle of lambda by, we get a maximum for two narrow slits separated by distance a. So for double slit experiment, there is a bright fringe at lambda by, but for a single slit, it is a dark fringe. So moving on to the both cases, one must understand that both D and A have to be quite small to be able to observe good interference and diffraction pattern. So this is the concept being talked about in the assumption when we started with the diffraction pattern, that the value of small a, small d, etc. is very less than capital D. And we also understood this using the example problem also, when capital D is approximately around, let us say 1 meters, then the value of small a and small d is around millimeters, let us say 0.5 mm, 0.1 mm, etc. So this thing also has to be understood that the value of both D and A should be quite small. Then for example, the separation D between the two slits must be of the order of millimeter or so. This was only the example which I was talking about previously. The width A of each slit must be even smaller, of the order of 0.1 or 0.2 mm. So this was the thing I was explaining you, it should be order of millimeters only. Okay, now let us move on. So this was the complete explanation of diffraction patterns. Now let us move on to some of the real life scenarios which we can even see with our own eyes, so that we can find out if a single slit diffraction pattern is occurring or a double slit diffraction pattern is occurring. So the basiest or the easiest example to find out a diffraction pattern is just to take two blades. So these are nothing but blades, and keep them so much apart parallelly so that a single very small slit is available here. Due to this slit, if we put these two slits and a light is passing through it, then we can see a diffraction pattern. So seeing the single slit diffraction pattern. So the equipment needed for single slit diffraction pattern can be found in most homes, that is two razor blades. So using two razor blades, you can find out the diffraction pattern, and one clear glass electric bulb, preferably with a straight filament. So quite evident for the single slit diffraction pattern to occur, either if we are getting a monochromatic source of light, it is okay, otherwise we will try to use a filamentous bulb only, which may have different 2-3 mixtures of wavelength. So one has to hold the two blades so that the edges are parallel. So as you can see, the edges are parallel here. If I try to make you like this, as you can see, the edges are parallel, and have a narrow slit in between. So as you can see, a narrow slit is observed in between. So this is the narrow slit being talked about here. The narrow slit is in between. This is easily done with a thumb and forefinger. So just using your thumb and forefingers, you can just place it like this, and you can find out a single slit diffraction pattern. Keep the slit parallel to the filament right in front of the eye. So you just need to keep it parallel to the filament, so that there is no distortion of any light. With slight adjustment of the width of the slit and the parallelism of the edges, so it has to be make sure that these both lines are parallel. If it is not parallel, and a slit is not forming correctly, and maybe we can't see the diffraction pattern. So with slight adjustment of the width of the slit and the parallelism of the edges, the pattern should be seen with its bright and dark bands. So quite evident, the diffraction pattern is nothing but a simultaneous dark and bright bands being available. So if we are quite peculiar, if we are quite right with the complete arrangement, then we can see the bright and dark bands being observed. Since the position of all the bands except the central one depends on the wavelength, they will show some colors. So if we can't find a monochromatic source of light, if it has a wavelength, then from the similar concept we understood for the example of effect of interference fringes, in which there was blue color light available at some position and then there was red color light available at some position due to the value of the different wavelengths. Hence the similar case scenario can be observed here, but because of central wavelength it is theta is 0, therefore everything is a mixture at passing midpoint, and therefore it is a bright central fringe. Apart from these positions we will see a consecutive dark fringes and bright fringes, but consecutive bright fringes may have some color with it. So this is again, so just let me iterate this line again. So with slight adjustment of the width of the slit and the parallelism of the edges, the pattern should be seen with its bright and dark bands. Since the position of all the bands depends on wavelength, they will show some colors. So they will show some colors here. Using a filter for red or blue will make the fringes clear. So if we make a filter for red or blue color, then it will make the fringes clear. The fringes will be observed much clearly, and with both filters available, the wider fringes for red compared to blue can be seen. So this is the similar case scenario which we observed in the concept of interference fringes in Young's double slit experiment. Similarly, both the filters are available, the wider fringes for red compared to blue can be seen. Okay, now let us move on to the more discussion on this concept only. So in this experiment, the filament plays the role of the first slit S, quite evident. So here this is on the back side of it, there will be a filament, or if I make it as a bulb only directly. So this is the source S being talked about here. So in this experiment, the filament plays the role of the first slit S. The lens of the eye focuses the pattern on the screen, that is the retina of the eye. With some effort, one can cut a double slit in an aluminium foil with a blade. So if you can see the if you take an aluminium foil and with much precision, if you can cut two slits like this, then a double slit experiment can also be performed. So with some efforts, one can cut a double slit in an aluminium foil with a blade, and the bulb filament can be viewed as before to Young's repeat the Young's experiment. So using the blades you can perform a single slit experiment, and for using aluminium foil with two cuts you can perform Young's double slit experiment. So in daytime there is another suitable bright source subtending and small angle at the eye. This is the reflection of the sun in any shiny convex surfaces, for example a cycle bell. Not direct sunlight, it can damage the eye and will not give fringes anyway, as the sun subtends an angle of half degree. So because the value of theta is very small, therefore it does not subtend, and hence in real life scenarios we cannot see a diffraction pattern observed here. In interference and diffraction, light energy is redistributed, quite evident, because the value of source is coming from single case and then it gives on diffract. So because from the word, how does the word diffract come? Diffract is nothing but the value of the mixture of light is being subtending at different angles, and hence it is known as diffraction. That is a redistribution of light energy is happening. So if it reduces in one region producing a dark fringe, it increases in another region producing a bright fringe, quite evident, as you can see at this point. At this point it was a mixture of all the light, but what is happening at this position, there is redistribution. If it is bright in some places, it is dark in some places. If it is bright in some places, it is dark in some places. So this is nothing but the redistribution of light energy. Please make sure it is only redistribution of light energy and energy is not formed. So there is no gain or loss of energy, which is consistent with the principle of conservation of energy. So again a conservation of energy in case of light also is being explained here. So let me stop the concept here only. So this is the end of diffraction patterns applications also. In the next lecture I will start with the resolving power of optical instruments, and that will be the end of diffraction. So let me conclude it here only. Thank you.